Yo, what up guys? iReapism here, and welcome back to another video. Today guys, I will be bringing you a new video regarding my random string generator I've created over the past few months. The purpose of this program is to generate a random string of characters. This can be used as a password generator, or testing how safe a string is from being cracked, or to generate long strings for encryption, which is very useful by the way, and it has its other uses. What makes this program unique is that you can insert your own symbols or characters for it to generate. This program will then display the probability of that particular string that generated from its character list. Through this, a lot of interesting mathematical properties arise through this program, and that's what we're going to be taking a look at today. Alright guys, so here's a look at the program and what it looks like. I have it zoomed in with the magnifier app on Windows, but basically, you just generate a random new string. You just click it, and on the edit tab, you can see what is being generated. So right now we have A through Z, and 0 through 9 numbers, right? And then on this side, it tells us the amount of permutations. So we have 26 letters, right? The capital letters, and then the 10 numbers, and then it'll add all of those integers, and then it'll tell you this is the probability and this is the permutations. Now, if you actually want the permutations, you can click the advanced information. I want to explain the really important set characters option. So right now we get to add our own custom characters. So for example, we can do like that. I think I did the asterisk, maybe that. There we go. So we press OK, and now it says +5. We added 5 characters, and we can see which ones we added all right here in this list. But these aren't the only characters. These were just on my keyboard. You can literally add characters from your own language, any language in fact. You can make up your own characters and add it to this list, which makes this program amazing because when you add the length to a string, so we're gonna be talking about just the capital letters and numbers. So when we start incrementing the length of the string, we're gonna start to blow up in terms of numbers, like how big the permutations is. Remember, the probability is 1 over the permutations. So there's 46,656 ways to arrange these these 36 characters in the length 3. As you can see, it's the math. And then once we get to this point, guys, what's really interesting is when we get to length string 13. And basically, this string that you see on my screen, you will never generate. And here's why. If every person on Earth were to generate a new string of length 13 from the second they're born to the second they die, the following is determined. So there is 7.125 billion people on Earth. So we're going to assume that there's 7.125 billion people on Earth, right? And the life expectancy of each person is 71 years. If we convert 71 years to seconds, we're going to get 2.239 times 10 to the 9 seconds, which is 10 digits long. With a string length of 13, the possible and all permutations of that length string of all capital letters and numbers is 1.705 times 10 to the 20th power. So, if you do 7.125 billion people and multiply all their seconds that they're alive for, you're going to get 1.595 times 10 to the 19, and that just is below the total permutations of the string length 13. Yeah, so length string 13 is pretty crazy when it comes to real life applications and putting that number in perspective. Now what we want to do is keep playing this game. We're going to keep adding to length and see how big this number gets. Now I'm going to skip a little bit ahead by scrolling, and this will enable me to increment by 5. And when we get to string length 198, we reach the upper bound. When we go any higher, we result in an infinity symbol. This stops giving us the value. And that's the double type limit for this language, and I think almost every language that uses a double type. And essentially, you will really never get this string. Like, the probability of you getting this string is so low. In fact, so if we take all of our permutations of a string length of 198, which is 1.405 times 10 to the 308, the following will be determined. So we have to try to put this number in perspective with our universe, and it turns out it's pretty hard to do, but I've tried my best to kind of jump to the point. So the amount of grains of sand estimated to be on planet Earth is roughly 7.5 times 10 to the 18. That's a pretty big number, honestly. That represents all of the sand on Earth. Now, unfortunately, we're not quite there, so we have to keep going. The diameter of the observable universe is roughly 8.8 times 10 to the 26 meters. Huge distance, right? Not quite there. The particles estimated in the known universe, all the particles, we're talking about electrons, quarks, all of that stuff, is roughly 10 to the 80. We're not quite there yet. So now it's gonna get tricky. We have to take the smallest meaningful length that we know in physics, which is the Planck length, which is about 1.6 times 10 to the minus 35 meters. A distance so small we couldn't hope to achieve viewing. The smallest time possible is when you take the Planck length and you put it over the fastest distance possible, which is the speed of light, and you get 5.3 times 10 to the minus 44 seconds. That's the smallest time possible. So now we have to get really small. A Planck volume is hg over c cubed to the 3/2 power, right? That represents a Planck volume, which is roughly 4.2 times 10 to the negative 105 meters cubed. Whoa, that's small, okay? Now we have to take that smallest volume and see how many of those we can fit against the largest volume, which is the volume of the observable universe. So the amount of Planck volumes in the observable universe is roughly 4 times 10 to the 185th power. So that small volume, how many of those are in the universe? How many of those small volumes can you fit in our universe? And that's the number. So if we let R equal 1.405 times 10 to the 308 Planck volumes, which is, 36 to the 198th power, that's the number of permutations for the string length of 198. So if we do R over 4.0 times 10 to the 185 power, we will get approximately 3.5 times 10 to the 122, which means you would need 3.5 times 10 to the 122 universes to get that number of Planck volumes. Wow. We made language to express our thoughts to one another. We have the largest possible volume versus the smallest meaningful volume, and yet they're so both inconceivably different. We can never reach a side of the universe, but we have this distance in front of us that we can never observe, which is ridiculous. Thanks for watching, guys. I hope you guys really enjoyed this video. It's taken a while to make, and unfortunately it's not the best quality you've ever seen of these type of informational videos, but it is one of my first. And if you are interested in seeing more stuff, I have 2 more videos like it, so you can take a look on the screen or in the top of the description. Thanks for watching, guys. Peace out now.